Hey guys, today we're going to be talking a little about Chapter 3. We're going to do 3.1 through 3.4 to start out. And in 3.1 through 3.4, we're starting to talk about projectile motion. Okay, when we talk about a projectile, whoops, it's a J, projectile motion. When we talk about a projectile, we're talking about something that is launched or thrown or sent through the air that's not driven by a motor, it's not being pulled or pushed once it's released. That means if you think about a ball being thrown, we throw the ball, as soon as it leaves my hand, the only forces on it are gravity and air resistance. Now for this simple level of physics, we're going to ignore air resistance in order to make the problems easier to approach and to understand the conceptual. In the long run, air resistance is real, and it is something that we do have to mitigate and manage. And that's going to be something you'd apply more in a calculus-based physics where you have the tools necessary to do that. As it is with this class, we're probably not going to spend any time doing air resistance. Just it's too dynamic of a problem. But we're going to talk about these projectiles as they're launched through space. One of the things we need to understand is whether they're launched up at an angle or they're launched off the edge of a cliff horizontally, they all follow a parabolic path, okay? It's important because there's a few things that we want to identify and understand. One, that here at the top, there's symmetry, okay? If you think about it from that perspective. That in the center of a projectile path, you should be able to find a high point, and then there would be symmetry about that point. And then we can use the three kinematics, which we talked about in the past. V equals V naught plus AT. Delta x equals V naught t plus 1/2 AT squared. And, of course, V squared equals V naught squared plus 2A delta x. These are our three kinematics, and we can use these anytime we're talking about projectiles. But because the projectile is not traveling in a one-dimensional path, it travels vertically and horizontally, we got to acknowledge that those two things need to be managed independently. This has to do with the concept of vectors, which we talked a little bit about, but we need to really dive in. When we talk about a vector, we're talking about something that has a size, a magnitude, but it also has direction. So when I talk about a velocity, let's say I'm going 13 meters per second. Well, I need to know where that is. And so we'll often use a drawing of a straight arrow to represent direction. The bigger the arrow, the bigger the velocity, and the angle of the arrow tells me the direction of travel. If I have something like this, where I have 13 meters per second, and maybe something like this, where I have, say, 14 meters per second, just a little bit bigger, to be able to add those two vectors together, I have to recognize that they're not in a straight line. So because they're not in a one-dimensional straight line, it becomes much more difficult to come up with an actual answer to what it means to add them. It won't be 27. It'll be bigger than 13, and it'll be bigger than 14, but it's not going to be 27. Well, it turns out that right here, if we if we connect the beginning of our travel, the tip of the first arrow to the tail of the second arrow, this diagonal, or this what we call resultant vector, is the result of adding these two vectors together. And so if we can learn how to calculate this measurement, we can figure out how big it is, what the actual answer for adding those two vectors would create. Now, a couple things we have to understand. When we talk about doing that kind of addition of vectors, we need to realize we can do it graphically by looking at this picture, but figuring out the numbers that go here and the angles, that's a little bit more challenging to do just visually. It's actually going to be a little bit easier if we turn things into the algebra and trigonometry that we know pretty well. And so that's what our first step is about. When we're dealing with vectors, we have what are called component vectors. And a component vector, okay, is the projected portion of a vector on the x or y axis. In other words, if I look at that 13 meters per second, my first vector there, I want to know how much of that is in the x direction, call that Vx, and how much of it is in the y direction, call that Vy. The reason that we want to do that is we can then add up the x vectors, x component vectors, and the y component vectors separately. In order to do that, I do have to know this theta here, though. So we're going to need at least one side and an angle, but that can help us, as we label that information, that can help us determine Vx and Vy. Excuse me. And then when we have multiple vectors that we want to add up, we can add the x components, we can add the y components, then recombine them using trigonometry. So for instance, let's just do a real quick one. Let's say I have 13 meters per second at, let's say, 30 degrees above the x-axis, and then I want to add a 14 meter per second vector at 0 degrees, or we'll call it due east. Okay, I want to go straight east from there, and so that means it's only got an x component, its y component would be 0. But let's go ahead and just break this first one down here. This 13, it needs to be broken down to its y component and its x component, Vx and Vy. Alright, so if I take, and I just use my basic right triangle trigonometry, the x component is the adjacent side, that would be a cosine. The cosine of 30 would equal Vx over 13. And the sine, I'm going to go a little bit faster, sine of 30 would equal Vy over 13. So I can calculate that with my calculator. Let me move this real quick. And I can figure out that, I better check my mode real quick. Yeah, I got to change my mode. I can figure out that 13 times the cosine of 30 is 11.2, and 13 times the sine of 30 is 6.5. So I got 11.26 and 6.5. So we'll go 11.26 and 6.5. So this is mostly traveling in the horizontal direction. But as I apply that other velocity of 14 meters a second, it's going to even more make a big deal out of this. So, you know, these might be Vx1 and Vy1. And then I have a Vx vector 2 and a Vx or Vy vector 2. So you got to find ways to label so you can distinguish which one's which. In the x direction, my second vector is 14. In the y direction, it is 0. I'm going to add my x's together. So I'm going to add the 12 to the 11.26 to get 23.26. And I don't add anything to the 6.5, so it stays at 6.5. Now, if I want to combine those up, okay, back, and I've got my Vx total and my Vy over here, I'm going to recombine them by Pythagorean's theorem to figure out my resultant vector. Okay, so 6.5, this is now 23.26. I can find that angle using the tan inverse. Right, the tangent of theta is the opposite 6.5 over 23.26. If you are not real comfortable with the trig, it's going to take some time, and you're going to have to spend some time. Come talk to me, and we'll work our way through the trig. But we're going to take the tan inverse of 6.5 divided by 23.26. Now, in fairness, I really shouldn't round it like this. I should just go up, select the 11.25833.025, and add the 12 to it. And that would be the best case, but I'm just trying to be a little quick here. We get 15.6. So the angle, the equivalent angle would be a 15.6. That means if I was, instead of taking this 30, if I just cut right along there, okay, that angle there, sorry, this angle down here, scratch that first one. The angle down here would be 15 however many degrees. 15.6 degrees. To find out how long that vector is, or what the total velocity would be, I'm going to have to add them using Pythagorean's theorem, which means I'm going to take the square root of my 23.26 squared plus my 6.5 squared. If I press enter, I get 24.2. So I know that this is a total velocity of 24.2 meters per second at 15 degrees above the x-axis, or north of east. Okay, That's how we pull these vectors apart, add them back together to create the new diagonal. Okay? The reason that we care so much about this has to do with how we measure and manage projectile motion, though. Basically, the idea here is that in projectile motion, when we would normally go and we'd build our x, we'd normally build our v naught, v, a, delta x, and t, and we'd solve our kinematic problems. Because it's two-dimensional, we're going to separate those two dimensions, separate the x from the y. And so we're going to create a separate set of these to be able to solve the kinematics. Now, we'll call that delta y and t. And this is really v naught x and vx, or sorry, y's. Dang it, Mr. Welch. These will all be y's, v naught x, vx, ax, and so on. There are a couple of things that we have to know are always true. For instance, when a projectile is moving through the air, let me see if I've got a projectile close by. Well, I've got this. All right. When a projectile is flying through the air, the horizontal forces on it that push side to side, the only horizontal force that acts on this object, once I let go of it, would be air resistance. We're going to neglect air resistance, and so because of that, without any forces pushing or pulling on it, the acceleration in the x direction will be 0. In the y direction, however, there is something that pushes or pulls on it. It will always fall towards the Earth, and if we're on Earth, we're going to accept that acceleration due to gravity is positive or negative 9.8 meters per second squared. Now, the reason I let positive or negative, it depends on whether we're calling up positive or down positive. There are lots of cases when you might make all negatives all downward motion be positive. But usually if there's up and there's down, we're going to let down be negative and up be positive. So there's a little bit of distinction there. The other thing that you need to understand is that because Vx and V naught x are the same, if there's no acceleration, then the velocity doesn't change. We actually can't use this Vx at all. So this actually narrows us down to only one equation in the kinematics. It's the second kinematic that we can use. It should look like this. This is only for the x information. And it gets even better. Because the acceleration is 0, this information is canceled. This is the only kinematic we can use for a projectile in the x direction. I've got a fly. I don't know if you can see that on the screen. Fly's flying around me. Anyway, this is our equation for the x side. If we know the initial velocity and the time, we can find the position. If we know the position and the velocity, we can find the time. All of these are direction-based, except for time. Time is independent of direction. So the time in the x is the same as the time in the y. They're going to be related to one another. Okay, hopefully that helps you with breaking it down. The truth is, when you're looking at the problems, if you break it down into v naught x and v naught y, and so on, you should be able to find something that you can solve for. And using that information, you might be able to solve for something else along the way. All right. Good luck. We'll see you in class. Keep in mind certain words like at rest and horizontal. Some of those words imply things like 0 as a value. So look for those kinds of hints and come and we'll chat about it. All right. We'll see you.